So in this video, we are going to take a look, ignore this, how we do binomial and Poisson distribution examples in Excel. So actually, I'm going to create a new file here, just so I can post this later, so you can kind of have it as a reference. So I'm going to zoom in so we can see what we're doing here. So we had some examples, some binomial examples. And I think the one that I have that corresponds to some of the references in the slides. Let's go look here. You get to, yeah, 6.7% of people are considered millionaires in the US. So this is net worth. Um, so let's think about NXP, right? So if I choose any one random person, the probability that they have over $1 million in net worth is 0.067. $1 million isn't quite what it used to be, which is a wild thing to say. But here, let's think about, I've got 100 different households. What's the probability that I see 10 of them actually be millionaires, right? So if I want to know the probability of this random variable X is equal to 10, right? I could type in that whole binomial distribution equation that we looked at before. So n factorial over x factorial times n minus that, all of that, right? But that's going to be a lot of work, and there's an easier way to do it. So there's this binom.dist function in Excel, and it basically has that formula built in behind the scenes, and all you have to tell it are four things. The first three are the typical ones that we were thinking about in all the examples we are looking at. So the number of successes will be the first thing. So that would be X. That's what we're trying to find the probability of. The number of trials. So put a comma. The second thing is the number of trials, N. And then comma, the probability that any one person, right? I'm looking at any one person selected that they were a millionaire. That was 0.067. The fourth thing that will tell it is to make this cumulative or not. So if I tell it 0, right, that's going to give me the probability of exactly being equal to 10. So I hit enter there. If I then said, okay, so, that's basically, if I, saves me a lot of time and effort, right? It plugs it all into that nasty factorial equations and it spits back out at me the probability. So what's kind of nice is I could actually set this up for different values of X. So 0, people have $1 million, 1, 2, 3, 4, 5, 6. Actually, can I copy this down? Forget the thing in the back now. There we go. I think if you hold, if you drag these down, let me see. So if you just drag it down, it'll copy it. If you hold Option, it updates it by 1 on a Mac. And then on a PC, I actually think on a PC, if you right click and drag it down, it gives you the options to like fill in the series. Right? So, anyways, you could just type these all out, right? But just I want to drag down to kind of show you that. So I'm going to use that binom.dist function. Here's my number of successes I'm interested in. Here's the number of trials. Here's the probability of success. Make it not cumulative, so 0. When I copy this down, I want to find the probability of all these different numbers of successes, but I'm keeping the number of trials and the probability of success the same. So I'm going to Command T or F4 on a PC, Command T on a Mac. I'm going to freeze these cell references. Hit enter. Now, if I copy this down, I'm using a different number of successes, but keeping the number of trials and the probability of success in one trial the same. So I can kind of see, it increases here. Now, if I was thinking about, okay, what's the mean of this binomial variable? Well, we said that's simply the number of trials times the probability of success. So 6.7, so 6 and 7 should be the most likely outcomes. And then as we move further from those outcomes in either direction, Notice the probabilities are getting smaller and smaller. Okay. Now, if I wanted to, I could highlight these, insert a bar graph. No, actually, I don't want to do that. I'm just going to highlight the probabilities, insert a bar graph, then kind of go here. Oh, it's command on a Mac, isn't it? Oh, no, it's control. Control on a Mac or right click on the PC, select the data, horizontal axes, or just, no, I forget some of the command shift or control shift, hit the down arrow. Now I've got my different values here. All right, so here's my kind of nice binomial distribution that I've got. Now, obviously, I kind of truncated it because really it goes all the way to 100, so it's going to have this really long right tail. But, by the time we get to 14, that probably is relatively close to zero. It's going to be even closer the further we go. So what if instead I wanted to find the probability that x is less than or equal to 10, right? Well, if I had all these probabilities, notice what could I do? I don't know why I'm putting it down here. Hold on. I'll put it up here. I could just add up all those probabilities from 0 to 10. I could also use that binom.dist function, tell it that number of success is 10, number of trials 100, comma, probability of success on any one trial, 0.067, make it cumulative. By making it cumulative, it'll essentially, behind the scenes, calculate the probability of 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, and add them all up for me. Sure enough, I get the exact same value. So nice kind of quick shortcut to find these cumulative probabilities from a binomial distribution. Okay. Let me think if there's anything else I want to say here. I think we're good. So the next thing we'll take a look at is a Poisson distribution. So for the Poisson distribution, we needed a lambda and then the x values we were interested in. So once again, I'm going to think about different x values from 0 to, I'm going to hold the option button. Let's just go up to 14 like we did for the binomial. And let's say, well, and actually I'm going to move this over just a little bit to give us a little more room because we'll come back to this. So let's say I want to know the probability that I see exactly, oh, what's a good example? So I'm looking outside of my window right now. And instead of a time example, I'll give you a space example. Every time I look out into the yard, I see a ton of birds, right? So let's say on average, when I look out the window, I see 8 birds, right? That's probably I'm probably under exaggerating that, right? So what's the probability if I look out the window now? I see 10, right? So the probability that I see exactly 10 birds when I look out the window, I could type in that Poisson distribution equation, right? We had lambda to the x times e to the negative lambda. But, I had to worry about, oh yeah, e is exp to the first, etc. So I'll use that built-in, instead, I'll use that built-in Poisson distribution. So Poisson.dist, kind of similar to binom.dist. I'm then going to say, okay, what's the number of successes I'm interested in finding the probability of? 10, comma, what's the mean? Well, the mean over my, I look out over my entire yard, that space, I usually see 8. And then I'm interested in just finding the probability of seeing exactly 10 birds right now. So I'll put a 0. It's not cumulative. Very similar to the binomial distribution equation. Hit enter, I get about 0.099. Okay. Now, I could go through and do a very similar thing I did for the binomial with the Poisson. And I think if you just shorthand it, it's got like some old functions where it was just Poisson, not dist. I don't know. The newer one is dist. I just try to get in good practice of using how it, the latest form of it. So Poisson.dist will tell it, here's our x value. Mean is lambda, not cumulative. I don't want lambda to update. So I'm going to Command T or F4 on a PC, Command T on a Mac, freeze those cell references that were referring to the lambda because that won't change. When I copy this down, my cell reference for the number of successes will So now I'm finding the probability that I see 9 birds, probability I see 12 birds, etc. Now, on average, I see 8, so that should be the most likely outcome. Notice, okay, actually 7 and 8 are the most likely here, right? And as I move in either direction, that probability is falling towards 0, okay? All right, so what if I wanted to instead find the probability x is, I don't know, less than or equal to 6, right? Well, if I had this set up over here, I'm like, oh, I'll just add up the probability I see 0, 1, 2, 3, 4, 5, or 6, enter. But if I didn't have this table set up and I didn't want to build this whole, probability table over here, I can use that binom.dist function, right? I can say, okay, look, what's the number of successes I'm interested in? Actually, here I just put a number of 6. I don't have to use a cell reference. Number of trials. Oh, sorry. I put a binom.dist. I'm on autopilot. Sorry. Poisson.dist. I was like, why isn't this? Okay, so 6, then the lambda should be the mean. I want it to be cumulative. So whatever value I tell this Poisson distribution or the binomial, when I make it cumulative, it starts with that value and then works its way to 0. So it includes whatever value I tell it, or it includes 6 here. Okay. Notice I get the exact same thing, right? So can make it cumulative just like that binomial distribution function. Okay. Um, I can also then just kind of play around with things. So this is where I have to be a little bit careful. So let's say I wanted to know the probability. Oh, let's say that it's in between 3 and 6, right? So that x is either 3 or above or 6 or lower. Well, I'm going to use, basically, I'm going to take the probability, write this out here. You don't look at me, hold on. There we go. I think I've got to switch this around here. So if I wanted the probability of x being greater than or equal to 3, less than or equal to 6, that's really saying I want the probability x is less than or equal to 6, but that includes the probability it's less than or equal to 3. So I actually want to subtract the probability that x is, well, I want to include 3. So I want this to be 6, 5, 4, 3, 2. No, sorry, 6, 5, 4, 3. But then starting at 2, I don't want to include these probabilities. So to find the probability I'm in between two values, right, I'm going to have to find two different probabilities, cumulative probabilities. So I can do this pretty easily in Excel, but I've got to be careful with these equalities, right? And I'll point this out in Excel here in just a second, but this is really what I'm looking for. So I'm looking for the cumulative probability of 6 minus, right, the cumulative probability of being less than or equal to 2. Because technically what I wanted was less than 3, but if I'm dealing with a number of successes, I can only ever see integers. So less than 3, I go to the next one down, less than or equal to 2. So let's go to Excel here. So what am I going to do? Well, I already have the probability that x is less than or equal to 6. I now need to find the probability that x is what, less than 3, which we said is the same thing as the probability that x is less than or equal to 2. All right, these are the exact same thing since we're dealing with integers. So I'll use not binom, geez, Poisson.dist. I'll tell it the value of 2. Right? The mean is lambda, comma 1, make it cumulative, and then define the probability that it's in between 3 and 6. I would just say, oh, what did I accidentally select? Okay. There we go. I'll take the probability it's less than or equal to 6 minus the probability it's less than or equal to 2, right? And I get 0.299. Now I can check this, right, using that sum function, because if I want the probability it's 3 up to 6, should get the exact same value. Now, where I need to be careful is maybe I look at this initially and I think, oh yeah, I'll find the probability that's less than or equal to 6, subtract the probability that's less than or equal to 3. Well, no. I've got the equality. I want to include 3 in this probability. So when I'm looking for that cumulative probability, I actually need to say, is it less than 3? But when I tell this 3, it includes it. So if less than 3, I have to go down to the next lowest value. If I don't, I get something that's a little bit off, right? So strictly less than, you would actually tell that Poisson distribution function in Excel, if you're using it as a cumulative way, you actually need to go down to the next lowest value. Okay. Um, that should cover. You can do a very similar thing with a binomial. And if we set it up like this, like if you have this equations kind of built in here, uh, I could play around with this for different examples. So maybe my lambda is 55, right? Now notice e to the negative, these are really low probabilities. But if I update like x, okay, that makes a little more sense. Well, I'm dealing with like 6 and stuff here that isn't going to make. So I'm going back to the one where it makes a little more sense. But you could play around with this and it will kind of update everything accordingly, especially if instead of like putting 6 here, I actually like put a cell reference in where I could update that number as well. One other thing that we could think about, it's kind of an easy setup, is we also said I had, so here's my Poisson. Actually, I could show you kind of an interesting way of doing this. So if I want the mean of a binomial, right? That was going to be, I take the number of trials and I multiply that by the probability of success. So let's say I had a really high number of trials, like 50,000. There we go, 50,000. Probability of success, 0.00001, right? Really low. Let's get a mean of 0.5, okay? If I'm interested in, actually, let's make this not quite as well. No, I did the same. 1, 2, 3. There we go. If I'm interested in, okay, what's the probability that instead of 5 out of these 50,000, I don't know, people, I see that they have some chronic disease, what's the probability that only 4 of them do, right? Well, I could use the binomial, right? So I go, okay, binom dot dist. Here's my number of successes I'm interested in finding the probability of. Here's my number of trials, probability of success, not cumulative. I just want to know the probability exactly for. Hit enter. Oh, because I put a period instead of a comma. I was going to say, what? All right. So 0.175. I could have also done the Poisson distribution equation. But remember, when I have a really high number of trials, right, I can look at that number of successes, but I can use an approximation for the binomial using the Poisson if I calculate the mean as the number of trials, when the number of trials is high, times the probability of success when the probability of success is low. If I do this, I should get something that's very similar, right? Out to here, if I round at the fifth decimal, I get the same value. Now, past that, it's a little bit different, right? But it's a really close approximation. Okay. So just another example of kind of how we would go from that binomial to the Poisson. I'll add in actually here. So that when you're reviewing this, here's our Poisson approximation for the binomial distribution. And then I'll have this work over here as well. So we'll kind of label this binomial, and we'll label this Poisson. So you'll have this for review when you go to complete your homeworks and Excel homeworks and eventually your exams.